Hello, everyone. My name is Narayan Banerjee. I'm a professor at School of Mechanical and IT Engineering, Yeungnam University, South Korea. First of all, I would like to thank Science Father for inviting me to deliver a lecture on the International Research Awards on New Science and Inventions Nation. My topic today is fabrication of a novel nano-network of metal, graphene, microporous carbon composite for high hydrogen uptake. Now, hydrogen is considered to be one of the important alternative energy sources for renewable technologies. In general, hydrogen is stored in three different methods. One is physical method, where compressed gas or cryocompressed or liquid hydrogen are stored in tanks, or in chemical methods where some solid state storage materials like physisorption materials, metal organic framework, porous carbon nanomaterials, various metal hydrides are used to store hydrogen, or you are having hybrid method where a mixture of physical and chemical methods are used. Now, the physical storage of hydrogen as compressed gas or cryogenic liquids involve safety issues. On the other hand, chemical storage and release system of hydrogen involves issues like high system cost, high operating temperature, and instabilities. Therefore, these reversible physisorption materials like geolites, metal organic frameworks, clathid hydrates, various carbon nanomaterials, etc., becomes very popular for hydrogen storage. Amongst them, high surface area carbon nanomaterials like micromesoporous carbon, graphene, carbon nanotube, graphitic carbon, metal carbon, composite porous, carbon hydride, composite, or various other carbon nanomaterials becomes very popular. And the reason is that it has several advantages like easy processing from natural resources, high gravimetric density, safer operating conditions, no volumetric or cryogenic constraints, high degree of porosity, large surface specific area, lightweight, effective reversibility, fast kinetics, chemical stability, among others. Now, there are some issues related to these current reversible physisorption materials because these are now having very low hydrogen adsorption capacities at ambient temperature and pressure. Generally, it is around zero point 0.6 to 0.8 weight% gravimetric capacity at 29 K around 100 atmospheric pressure. On the other hand, Department of Energy US set a criteria for the system gravimetric capacity of almost 5.58% by 2025 for personal transportation vehicles at moderate temperature and pressure. So therefore, to overcome this, we need to increase the specific surface area of these carbon nanomaterials by tuning its physicochemical properties. We can decrease the pore size and increase the pore density in microporous carbon. We can increase the local curvature in graphene to increase the active adsorption sites. We can create some 3D network of graphene oxide layers with multi-layer carbon nanotubes. Also, we can fabricate some graphitic carbon, mesoporous carbon network, or we can synthesize some metal incorporated porous graphene nanostructures. But still, there are some issues remain. These are some of them are the costly and toxic chemicals are used for these materials for carbonization. We need high temperature treatments for activation. Most of them are solution based techniques and therefore not compatible to modern solid state CMOS IC fabrication techniques for practical applicability. Therefore, we are planning to fabricate a metal incorporated graphitic microporous carbon by a vacuum-based technique. The objective is that in the graphitic micro or mesoporous carbon, we can have very high surface area from the pores or very high H2 binding energy in the graphitic network, which will enhance the hydrogen uptake capacity. On the other hand, the metal incorporation will increase the polarization and hybridization of metal and hydrogen to increase the hydrogen binding energy. But the graphitization process by vacuum-based techniques generally use electron beam on or ion beam irradiation on some carbon films or amorphous carbon films, but which is highly time consuming, therefore unsuitable for volume production. We need some low cost, high throughput process for practical applications, and one of them is sputtering of metal nanoparticles on amorphous carbon film. So the importance is that the sputtering technique is CMOS compatible, large area fabrication is possible, it is cost effective, it is an ambient temperature process, therefore suitable for volume production for practical devices. Also, the number of graphene layers can be controlled by controlling the sputtering parameters. And this microporous carbon terminated with graphene walls can have very high binding energy at the local curvature. Therefore, in our process, we have used a two-step process where first step, we used a thermal evaporation technique to deposit some highly thin, few nanometer, 5 to 7 nanometer thin film of amorphous carbon and on silicon wafer, and then we transferred it to a sputtering chamber to sputter some metal nanoparticles to create this graphitic microporous carbon network. And this is the fabrication technique by lithographic process for hydrogen storage or hydrogen storage testing devices. So we started with silicon wafer, then deposit amorphous carbon, then using some masking, we sputtered deposit some graphitic microporous carbon network in some specific spaces, and then finally we package the device. And this is the device structure, and this is the experimental procedure and experimental schematic. Now, these are some results and discussions, some TM and Raman images of the amorphous carbon, and we can see the TM image of some microporous carbon before graphitization using some low sputtering parameters. And this is showing the typical Raman spectra of an amorphous carbon and microporous carbon, which is only showing a small D peak, which is typical of amorphous carbon network. Now, when we increase the sputtering parameters, we were able to fabricate some graphene layers on this microporous carbon network. You can clearly see some bilayer or tri-layer graphene formation in the graphitic microporous network. So here also we check the lattice spacing, which is matching with the graphene layers, which is d-spacing of graphene layers, which is 0.34 nanometer, and this is showing typical Raman spectra of the 2D peak of a two-layer or bilayer graphene, which is clearly showing 4 components: D, 2D1B, 2D1A, 2D2A, 2D2B. 4 peaks are clearly observed. This is the signature of a bilayer graphene. Now, when we increase the sputtering parameters slightly, we are able to obtain some 3-layer graphene. Here also we are able to see all the 4 components of the 2D peak, but the intensity is decreased. So this is obvious, because when we increase the number of layers from bilayer to multi-layer, the 4 components will ultimately merge into two components, which is observed in this multi-layer graphene, where we increase the sputtering parameters. Either we increase the sputtering time or increase the sputtering voltage. So we are able to obtain multi-layer graphene, and this is showing the typical 2D spectra of multi-layer graphene, which is actually composed of two components. And this is the D and G peak, which is typical of the carbon network. And what we observed is that when we increase the sputtering voltage, number of graphene layers are increasing. On the other hand, when we are increase the sputtering time, the ordering of the graphene layer increases. Here you can clearly see that the multi-layer graphene, with increasing the sputtering time, highly ordered graphene layers are created, and when we increase the sputtering voltage, number of graphene layers are increasing. And this is showing typical line intensity spectra to show the proper despacings, actually corroborating the proper graphene layer formation. So this is actually showing some HRTM image of the metal incorporation inside the graphitic microporous carbon network. These are some of the metal nanoparticles you can see. Here you can see the HRTM image of 3 layers of graphene, and this is showing metal incorporation inside the graphene layers. Now, one more thing is that when we increase the sputtering parameter beyond a certain limit, we are observing some metal film formation or covering of the entire graphitic microporous carbon by metal film. So therefore, this table is showing that when we are having a very low sputtering parameters, no graphitization is observed. When you slowly increase the sputtering parameters, average number of graphene layers are increasing, and ultimately beyond a certain optimum limit, the sputtering parameters, beyond a certain optimum limit of the sputtering parameters, either some metallic film formed, which actually deteriorate the hydrogen storage capability. Therefore, we stick to our sputtering parameters up to this optimum value. And one more thing which we actually corroborated, that generally when we put this amorphous carbon film inside a high resolution TEM system, because of the high energetic electron beam is irradiated on this amorphous film, this electron beam sometimes can create this graphitic network. So therefore, to prove that this graphene network is not because of this high energetic electron beam, but because of the sputtered particles, we actually did the TM imaging at a very low electron beam energy, 80 keV instead of 200 keV, and we still able to observe this graphene network. So this is clearly corroborating our observation that these graphitic microporous carbon are fabricated through sputtering technique. Now, the mechanism of this graphitic microporous carbon network is basically a dual effect of simultaneous activation and graphitization. Initially, the amorphous carbon network, when we used under the sputtering system, due to the use of sputtering plasma and high energetic sputtered particles, some of the hexagonal bonds are broken into heptagonal or pentagonal bonds, creating some local curvature. And with further transfer of the sputtering energy, this local curvature is converted into graphene layers. And finally, creates some long-range graphene layers inside this microporous carbon network. And finally, this is creating this metal incorporated partially graphitic microporous carbon terminated with some flat curved graphene layers. So therefore, the dual effect is activation and graphitization. Activation is done by the sputtering plasma, which consists of ions, electrons, charged subatomic particles of argon ions, which remove some loosely bound surface atoms to create disordered micropores. On the other hand, graphitization is done by the high energetic ions, electrons, or negatively charged sputtered particles, which collide with the carbon atoms via knock-on elastic collision process or knock-on graphitization process to transfer necessary energy for this structural ordering or graphitization. Now, we also did the theoretical analysis of this sputtering system or the sputtering plasma to observe whether these sputtering particles have enough energy for activation or graphitization. For that, we first considered the energetics of the sputtering system. Generally, the total energy transferred to the substrate during sputtering consists of kinetic energy of the sputtered atoms, which is the primary contributor for the knock-on effect, then kinetic energy of ions and electrons originating from sputtering plasma, which is the secondary contributor for this graphitization. Third is the kinetic energy of neutral particles reflected towards the substrate, is the least contributor towards the knock-on effect, and the plasma radiation energy, which is least contributor for the graphitization, but the main contributor for activation for porous carbon network formation. Now, when we did the theoretical analysis of the first contributor, which is the kinetic energy of the sputtered atoms, using some theoretical analysis, we observed that the energy of the sputtered atoms vary from 0 electron volt to almost 250 electron volt. On the other hand, the threshold energy for this knock-on graphitization or structural evolution of the amorphous carbon is 10 electron volt. Therefore, we can say that considerable amount of energetic atoms exist near the substrate surface whose energies are higher than the threshold energy to manifest the knock-on graphitization. Similarly, we did the theoretical analysis of the kinetic energy of ions and electrons originating from sputtering plasma, and we see that the energy is varying from 10 to 20 electron volt. So it is not contributing too much for the structural ordering, but mostly contribute only to the micropore formation. Similarly, we did the theoretical analysis of the kinetic energy of neutral particles reflected towards the substrate. Here also we have observed that the energy is varying from almost 0 to 270 electron volts. So considerable amount of reflected neutrals are existing near the substrate surface whose energies are higher than the threshold energy to manifest the knock-on graphitization. And finally, we did the theoretical analysis for the energy distribution of plasma radiation, and we see that the plasma radiation average energy is around 2.7 electron volt, which is less than the threshold energy of the graphitization of amorphous carbon, which is 10 electron volt. Therefore, this mainly considered to be contributed to the micropores formation. Therefore, to sum up, primary contributor for structural ordering is the sputtered metal atoms having kinetic energy over threshold and reflected neutrals having kinetic energy over the threshold. The secondary contributor for structural ordering is the high energetic electrons originating within the plasma having kinetic energy over the threshold, and primary contributor for the micropore formation is plasma radiation energy. Now also we see that when we increase the voltage or we see that when we continue sputtering, we observe that the ordering of the graphitization is increasing. So this is also because of some potential energy minimum is created that is creating a cascading effect for longer order three-dimensional graphitization of the samples. Also, with increase in the sputtering parameter, the structural ordering is also increasing, which can also be theoretically analyzed. You can see that when increase the sputtering voltage, the sputtering current is increasing, which is also increasing the graphitization to increase the number of graphene layers as well as improve the ordering. Now we did the hydrogen storage testing of this physics option materials. For that, we increase the differential resistance resistance measurement. So what we did is that we put our device into a hydrogen flow system, and we flow hydrogen mixing with some nitrogen and test the resistance in the presence of hydrogen and in the absence of hydrogen. And we observed that in a hydrogen flow of 20 SCCM, as the number of graphene layers are increasing, the resistance or differential resistance is decreasing. So with increasing the number of graphene layers and with increasing the ordering of the graphene, hydrogen storage increases. So this is what we observed here. So what is the reason behind this? So these are some of the other results. You see that with different sputtering voltage, the increase in graphene layer is increasing the hydrogen storage. Now, this hydrogen storage mechanism is a fourfold mechanism. Generally, the hydrogen storage and electron hopping in the micropores of activated carbon, that is one reason for this hydrogen storage. Now, the kinetic diameter of HH nucleus distance is 0.07 nanometer, whereas the pore dimension is around 2 nanometer or less. So therefore, a large fraction of hydrogen molecules are adsorbed within these pores via formation of dipoles in hydrogen molecules through London dispersion forces. Similarly, in this graphitic network also, the hydrogen storage occurs in this graphene network via this dipole formation. And because of this dipole formation, the electron hopping increases. And as the electron hopping increases, the resistivity decreases. That means more you have the graphene layer or more you have the micropores, more dipole formation occurs. Therefore, more and more hydrogen molecules are attached through this dipole formation. Therefore, the resistivity is decreases and therefore increases the electron hopping. So this is the reason with increasing hydrogen storage, the resistivity of the system decreases. The third reason is also the hydrogen spillover on metal nanoparticles and corresponding hydrogen diffusion within the graphene layers. Generally, we know that in transition metals, hydrogen molecules is broken down and then they spill over into this graphic network, and therefore this absorbs more hydrogen. And finally, the formation of graphene from graphene or hydrogenated graphene. This is by breaking of the pi bonds in graphene during hydrogen uptake to convert into hydrogenated graphene. So because of this fourfold reason, this system is giving you very high hydrogen storage capability, and therefore this can become a very good hydrogen physics option materials. Therefore, in conclusion, we say that this amorphous carbon can have several advantages. It can process in a simple, cost-effective manner. Large area fabrication is possible. Therefore, possibility for volume production is there. It is also possible for ambient temperature, vacuum-based techniques. Therefore, this is clean, eco-friendly, and therefore CMOS IC fabrication compatible. On the other hand, the sputtering process is creating microporous carbon. Also, sputtering is creating this highly ordered graphene network, also creating some local curvature, which is improving the hydrogen storage capability. And the metal incorporated graphene is also increasing the hydrogen binding energy. And this is the schematic of the formation of this physics option material, metal incorporated graphitic microporous carbon. and showing very high hydrogen uptake capability. And in terms of future direction, we want to control the graphene layer up to mono to bilayer, and also we want to use some other metal nanoparticles which is having high sputtering threshold and low sputtering yield to control the sputtering parameter as well as the graphitic network more easily. We can also use some DCRF and pulse sputtering technique to control the graphitic network more easily. This can also be used as hydrogen storage as well as hydrogen sensor devices, and similar method can also be used for other gas sensor applications. And we can also use a combination of sputtering and graphitic or graphitization using some catalytic nanoparticle for catalytic graphitization to enhance the active area. And these are some of the papers and patents for this system, and this is the acknowledgement for National Research Foundation Korea. Thank you very much for your attention.